Thanks for allowing me to do this live, knowing that that it could have been slightly less obvious to work out, as it did. And also a big cheers to all the Australians and all the ones on the whatever coast which is furthest away for still being awake. So can I? No, I guess I. How can I make this? Here. Ooh. Nope. Anyway, so somebody's recording this, I guess, for on the video later. All right, I'll just start, okay? So my name is Thias Guns, and I'm very happy to have been invited to talk about our work on hybrid prediction and constraint solving, which is, I believe, a very exciting area. So this is joint work with Jay, Sojianta Mandirox, Kanoy and Maxime Lamba, who are PhD students in my team, and also Peter Stuckey, who I've seen here in the session, and Emir Demirovic at Melbourne, and Emir is now at TU Delft. So combinatorial optimization, of course, I do not have to explain this to you. It's about solving constraint optimization problems. Well-known examples being vehicle routing, all kinds of scheduling problems, configuration problems, graph problems, and so forth. Now, if you look at current constraint solving practice, and Maria has gone in this direction as well with her talk, then you could say that current practice is to first model the problem, and so to write down the problem specification in an explicit way, and then to use a solver to find the solution. But if we look at what goes on in practice, then we see, and you can ask the question, where does this model actually come from?
Can I interrupt you?
Yes.
I thought it was just me, but I asked a few other people. We can only see your face, not the slides.
Really?
I thought that you were improvising and you were
No, not at all.
Okay, so it's not useful.
Yeah.
Thinking that he was waving at the slides.
Oh, that's it. That's it.
Is this
yeah.
better?
Yes. Yes.
Okay, I was also wondering because I didn't see myself. So I had this beautiful image of an iceberg, which will become more clear to you a bit later in the talk. Some random images of constraint optimization problems, not improvised. And so where does the model come from? And so this is, of course, written by an optimization expert. But where does this optimization expert get the model from? Well, from lots of sometimes painful discussions with domain experts who in turn have been in contact with stakeholders and so forth and so forth. And I hope you agree with me if I argue that this process in some way is often too rigid and too static. And part of the reason is because and this is actually backed up by social sciences. So knowledge actually exists in two parts. Namely, there's explicit knowledge and there's implicit knowledge, right? And the explicit knowledge is a knowledge that we can actually write down in a formal language, such as a constraint satisfaction specification. But there's also a lot of implicit knowledge in any kind of organization. So this is something called tacit knowledge. And the question is, how can we make our approaches also capture this implicit knowledge? And more specifically, the approach that I will be using is we're looking into different ways where we try to see, can we actually learn some of the implicit knowledge from data and then make this part of the constraint specification of the constraint optimization problem. And so in this talk, I will present 3 different approaches that all fit within this theme. So there's part implicit knowledge that we're trying to learn and part explicit knowledge constraint optimization problem. So the 3 examples, the first one is about learning tacit knowledge, more specifically user preferences or social conventions regarding what is a good solution and what is not a good solution. The second part will be about perception problems. So what if part of your data isn't actually fixed data, but is, for example, image data. And then finally, when the constraint optimization is done within a complex environment where part of the input has to be predicted, for example, predicting energy prices and so forth. All right, so I'll go in each of these 3. So the first one is about user preferences, about that type of tacit knowledge, and the work is based on the paper which last year won the best student paper award at CP, called Vehicle Routing by Learning from Historic Solutions. And so in this project, we're actually working together with a relatively small vehicle routing company in Brussels, and they're very proud on being a very green company, both in their hiring processes and types of people that they work with, but of course also in their operations. And that means respect for the drivers. They drive CNG vehicles so that their emissions go down, and so forth and so forth. Now, when we visited this company, they have a route optimization software. And so they have a route planner, fills in all of the data, and then they press optimize. But then they absolutely dislike the solution that comes out, and they start making lots of manual changes based on, for example, knowledge. And this is in urban environments like Brussels and Antwerp. So based on their knowledge of what streets should or should not be driven into. Also things like, so they often drive at night, and they actually prefer to be at some clients before a certain time if they can, but if not, it doesn't really matter. Also, they take into account who drives which vehicles, because some of the drivers know Brussels better, but in other cases, they're in general better drivers, and so forth and so forth. So they have all of these types of tacit knowledge that we tried to formalize, and we tried to write it all down, but we failed. And that's why we thought about, okay, maybe we can learn this. So the goal is to learn these preferences of how the vehicles should actually drive, so what the sequence of stops should be, so that we can reduce the manual effort. But also, what they say is that their preferences, that, you know, it used to be that we did this and this, but now we do this and this, and these kinds of explanations. And so ideally, if we can have a system that can learn from the manual changes that they made, then we could build a pipeline that automatically adapts to these changes over time. That's a bit a bigger goal. All right. Now, if you talk about machine learning, people often start thinking about big data, deep learning, and so forth. But in this case, we have small amounts of data. So from an operational perspective, we have 6 months of data, which for them is a lot. But from a machine learning point of view, it's 26 weeks. And it's mostly weekdays. So it's actually 130 weekdays. So we have a training set of 130 instances. And that is not a lot. So what is it that we did here? Well, so we want to learn user preferences in terms of the routes that should be driven by observing the kind of routes that they manually made. Now, I've worked a large part on data mining as well. And if you look at data mining at the mobility mining literature, then there's a number of works that for a single vehicle predict where that vehicle is going to stop next, or which turns it is going to take. And for this, they often use Markov models, sometimes hidden Markov models, some plain Markov models. And so the question that we ask here is, if you have in the machine learning community all of this work on predicting where a single vehicle can go, then maybe we could use similar techniques to learn how to do a routing over a set of vehicles all at once. Right. And then, of course, if we can learn these preferences, the next question is, how can we now actually optimize over these preferences using constraint solving, because we have to satisfy the capacity constraints and so forth. So, so the key idea of the learning part and how to do the predictions is that we want to have some kind of probabilistic model that can capture the preferences. If we would have such a probabilistic model, then we can estimate, we can evaluate what the likelihood of a routing solution is. And let's say that we have a routing solution consisting of 3 routes. Each route is a sequence of stops. If we can evaluate the probability that this routing would be a preferred routing, so how likely is this routing to be to interest of the end users, then that would be a good approach, because then we can search for the most likely routing. Now, how do you do this? Well, if you look at an individual route in a vehicle routing problem, so just a red one, for example, then this is a chain of stops. And a chain of stops means that we can for example, approximated by interpreting things as a Markov chain. And what we actually do is, even though we have multiple vehicles, and we can daisy chain these routes all together in one big route. And then one routing, one VRP solution can actually be represented as one long route. And for this route, we can devise different kind of probabilistic models. And the most simple one, because now we have one big route, so there's a sequence and we want to evaluate the probability of it. So in its fullest expressivity, the probability of the whole routing would be the probability of the first stop times the probability of the second stop given the first stop times the probability of the third stop given the second and the first, and so forth, right? So that's one way to compute this joint probability. Of course, then we'd have to estimate what all of these probabilities are of these individual component probabilities to get the joint probability. However, from a Markov perspective, so if we treat it as a Markov chain, then we could say we're going to make a first order Markov approximation, meaning that we're going to assume that every state only depends on the state before it and not on all of the states before that, right? So that means that now the probability of our daisy chained sequence is the probability of the first stop, which is the depot, which is always the first stop. So this is simply 1, times the probability of going to the second stop, given that you were at the depot, times given the depot, the probability of going to the third stop, given that you were at the second stop, times fourth stop, and so forth and so forth. All right. Now, this probability computation is first of all quite simple, and estimating these transition probabilities now becomes much more feasible. So the goal is to learn a probabilistic model of this first order Markov model. And what we can do is we can estimate these transition probabilities, so the probability of going to stop Y given stop X, by observing the transitions of the actually driven routes in the data. Okay, so if one day we have a routing that goes from A to B to C, then the transition probability of going to B, given that you're in A, is increased by 1, right? So we can compute these probabilities by taking the relative number of observations of that transition in the data. And so we count how many times somebody went from A to B, and we divide this by the total number of routings that we've had. And this actually gives us a probabilistic transition matrix. And here on the right is one visualized. So the darker the gray areas, the higher the value is to 1, and the lighter gray colored, the more closer to 0. And as you can see, it's already quite sparse, right? So in the worst case, this would be a fully connected graph, but it is not. And so that shows that even such a simplistic first order model already can capture a lot of the structure that is apparently in the solutions. Okay, so now we have a probabilistic model, this Furcos model. Now what? Well, the goal is to find the maximum likelihood solution. So we want to solve a VRP problem where we change the objective function into finding these maximum likelihood. So solving this probability, this product of probabilities. Now, a standard trick when doing probability computation is to take the log likelihood, meaning that all of your products become nice sums. And so the maximum of the probability over each of the pairs in the sequence, their probability equals the maximum of the sum of the log of that probability times the decision variable of whether that transition was taken. All right. Now, this is actually super similar to the standard VRP objective function. And so we typically minimize the sum of the distances over each of the arcs. And what we now do is we will minimize the minus log probability of each of the arcs. So this is great because it means that we can use any standard VRP solver. We only have to compute our probability, our transition matrices, plug them in, and we can find the maximum likelihood. So most preferred solutions. Now, we don't have to stop there. All right, so it's always good to go back to either the learning or the solving and see whether we can improve it. And so the question is, can we do the learning better? Now, typically when people apply Markov models, they have one big transition of states, and they're building the transition matrix over all of that. But in this case, one sequence for us is one routing. But we have different kinds of routings. Namely, our training data is over 6 months of data, and every day we have a different routing. And furthermore, each day, the set of customers that is being visited is slightly different, because they have some fixed clients, and then you have some variable clients which just call in when they need a pickup or not. So each day, the number of clients is different. And also, as I said before, they indicated that their preferences can change over time. And so if we want to find solutions that actually match their current predictions, we need to make sure that our model also adapts to such changing preferences. And so we made 3 adaptations to the learning. The first one is that instead of just taking each of the historic instances, taking their count and making it relative, we can actually give different weights to different instances. For example, the instance of yesterday, the kind of routing that they drove yesterday, we can give it a much higher weight than the one of 2 days before. And the one of 2 days before can have a lower weight again, and lower weight again, and lower weight again, and lower weight again. Right? So depending on the time, we can decrease the importance or how much evidence that instance provides to our probabilistic model. So we can do this, this weighting by time, but we can also do the weighting by similarity, as I wrote here above. So the sets of clients can differ from day to day. And so we could also say, okay, those days that were most similar in terms of client set, those should provide more evidence, and the other ones should provide less. So that's one thing. Another thing is that we know that some of the stops are rarely visited. Okay. Now, this can be problematic because we're dividing the frequency here of the transition by a number n. And in the worst case, some transition has never been taken, but it should be considered by the optimization problem for this instance. Otherwise, it cannot make a route, for example. Right? And so one traditional way of overcoming these few observations or even the zeros is to do Laplace smoothing. So with Laplace smoothing, you add some virtual visits, and so you add an alpha factor to each observed frequency, and then you also adapt the divisor by that. And so the result is that you won't get zeros in your matrix, but you will just get small values, meaning that the VRP solver can still will still be rewarded for taking that edge. Okay, and then lastly, another thing is that in case there's new clients being added into the sets, that means that there will be no prior probabilities. So it means that in this probabilistic model, they will get a uniform probability of going from one to the other, and thanks to the Laplace smoothing. But uniform may not be the right kind of idea, because we know that this client will be closer to some and further away to others, right? So instead of assigning uniform probability, maybe we should assign it a probability based on the distance it has to the other stops. And so what we can actually do is we can mix the probabilistic model that we learned, the TIJ, with the actual distance model. If we properly normalize this, then we can actually take a convex combination of the probabilistic preferences and the distances, and then we can optimize this. We tried all of these variants, and here in the middle you see some results. So if we just optimize based on distance, then we have 2 ways of evaluating quality of a solution, namely in terms of the arc difference. So how many arcs are visited in the 2 different routes versus route difference. So how different are the routes themselves? And we see that if we optimize just over distance, the solutions that we had are quite far from the ones that they actually drove. And if we use our learning technique with different kind of weighting schemes, then this is improved. And in general, doing the time weighting seems to be somewhat better, right? So the key idea, is there a takeaway? No. So the key takeaway is that this approach can work for any VRP solver, and that it's better than traditional approaches, and there's still a lot of freedom in how you learn these preferences. Okay, so that was the first part. In the second part, we're not going to learn implicit preferences, but we're going to assume that part of the input is data such as images or text or audio. And the example that we're going to take, since sudoku is supposedly the constraint programmer's favorite toy example, we're going to look at visual sudoku. And so what changes when we're dealing with visual sudoku? Well, now we don't have a grid of given numbers, but we have a grid of images. So for every cell in the grid, it's either empty, so white pixels, or there is some kind of writing. And in this case, this is a 32 by 32 image of grayscale pictures. They're actually from the famous MNIST dataset. And so what you first have to do is you first have to take the image, so the raw pixels as input, determine what kind of number it probably is. And you can use some standard convolutional network for this. If you use this network, then you will get a probability for each of the possible digits. So the probability that it's a 0, probability it's a 1, that it's a 2, and it's a 4. If you then take the argmax of that, in this case, it would correctly classify this image as being a 6. You can give this, you can add this to your specification, call a CP solver, and get a full solution. All right. So if we build some sudokus where we replace the digits by these images, what happens? Well, if we use a baseline classifier of 94%, so a decent but not particularly good classifier, then we see that actually 48% of the grids cannot be solved. And so even though only about 5% of the images in expectation will be wrong, we see that it results in 48% of the grids becoming unsolvable. And so if you extrapolate at the entire cell level, it's 15% and 14%. Basically, this says that doing the predictions independently of the solving is not a good idea, because if the solving says unsatisfiable, you don't know what to do. All right. So this work was inspired by the visual sudoku problem in the SATnet paper. And in that paper, they actually looked at integrated end-to-end learning. So can we learn a classifier of the images based just on the solutions? But the question that we're asking here is, why do we need to learn based on just the solutions? Why do we need to learn both the problem structure of the sudoku and then the image classification? I mean, we have plenty of solvers for which solving sudoku is trivial. So can't we just use the knowledge and know that the explicit knowledge is that we're solving a sudoku, and then focus on the learning part? And so we want to keep explicit what's explicit, the constraints, and keep implicit what's implicit, namely the learning. Okay, so, and we're actually not going to improve the learning. We just want to get better solutions. And given a classifier, can we use this classifier in a better way to solve this visual sudoku problem? So by now, the way I explained it, it might have become obvious that instead of taking the argmax and only using the most likely image here, we actually want our constraint solver to reason over each of the possible probabilities, what that specific cell might be, and what the other cell might be, and what the other cell might be, and so forth. All right, so we don't want to have the argmax outside of the constraint reasoning. We want to have this argmax as part of the constraint reasoning. So the argmax for each individual prediction, X here is the image. So each prediction is a function over the image, and this one equals to an argmax over the probability for each of the separate digits. Now let's put this into the CP model. Right, so in this case, what we want to do is, over all of the images that are known, and all of the given images, we want to minimize for each of the possible digits that it can be, the minus log likelihood of that prediction. right? So all of this underlined in blue is a constant, and this is just the minus log probability of that one, for example, the P0 or the P1 or the P2. And then we multiply this by what digit was chosen by the solver for this specific cell. So Sij is the decision variable. The problem is still a standard Sudoku. So in each cell, the constraint solver will fill in one digit, and then we're taking what the probability of this digit is according to our neural network, and we want to find a solution that maximizes this probability, so minimizes the minus log likelihood. And so the key effect is that now the maximum likelihood, or let me rephrase that. So if we would take the maximum likelihood prediction for each individual image, and this would be a valid Sudoku, then it will also be the one that's found by this objective function. However, let's say that you take the argmax and that your CP solver finds that this is not satisfiable. Well, by putting the probabilities into the objective function, it will now forbid, it will say, no, this cannot be a solution. So let's search for the next most likely assignment that is feasible by all of the constraints. All right, so that's actually what's going on here. We're finding the maximum joint probability solution, and the constraints forbid some of them. So in machine learning terms, the solver does joint inference over all of the predictions. Okay, now a bit more about the predictions. So what's wrong with these individual predictions, or what can be some of the issues that are happening here? Well, one thing is that each image is learned independently, and that's because an 8 is an 8 and a 9 is a 9. But when they're in a Sudoku, whether something is an 8 or not, it also kind of depends, or it has an influence on whether there is another image on that row that is also estimated to be an 8 or not, right? But the training, the way it's done, is each image is learned independently. And so there's no penalty for a certain image having like a super high likelihood of having an 8 and also a super high likelihood of being a 9. Okay. Now this is related to something called calibration in the machine learning community. So the fact that your classifier may actually be overconfident in some classes. And if this overconfidence happens, then it will actually distort the joint inference. So it will actually, the solver will think, oh, this prediction must be true because it has such high probability, while in fact it is not. Now this problem is something that we can overcome. Also in the machine community, there's been work on this, on learning calibrated classifiers. And so we've looked at 3 different kinds of calibration: temperature scaling, vector scaling, and matrix scaling. And we see that if we calibrate the predictions before we give it to a solver, first of all, the negative log likelihood decreases, which is what we want. And second of all, the test accuracy. So if we evaluate the Sudoku solutions on, no, this is not the Sudoku solution. This is the predictions. So if you evaluate just the accuracy of the predictions in itself, then we see that they also improve. And if we then feed this into the visual Sudoku system, so that those are the 3 images below, then we see that being uncalibrated or doing temperature scaling results in the same kind of solution. So temperature scaling doesn't have an effect. But if we do matrix scaling, which is the most complex type of scaling, then we see that the solutions found by the CP solver actually become better. Yeah. So by taking into account that predictions standardly are uncalibrated and making them calibrated, the joint likelihood solution that we get after CSP solving actually improves. All right, so that's how we can improve the learning. Now, let's not stop there. Let's not stop there, and let's ask whether we can also do the solving any better. Are we using all available information when we do the solving? And there's one piece of information that we're not using because we typically don't use it. And that is that a Sudoku puzzle has to have a unique solution. If it doesn't, then you're screwing the people that are trying to solve it, because they will have to make a choice and they cannot fully determine it based on pen and paper. So by definition of a Sudoku puzzle, it has to have a unique solution. Now, this is something that we typically don't need to take into account. And so it's also not in the constraint model that we currently have. In fact, this is a second order constraint, namely that there is no other solution that satisfies this input. Now, when we're dealing with this maximum likelihood kind of estimation problem, here, this is a property that we can use. Because what can happen? Well, it could be that the maximum likelihood assignment to each of the images that respects all of the constraints, it could be that if we just project it back to the input images and we ask how many solutions do these maximum likelihood digits have, it could be that there's multiple solutions returned. Now, if there are multiple solutions returned, then we know that whatever prediction is given to each of the images is incorrect, right? We know that this maximum likelihood solution cannot be the intended solution because it should only have one unique solution, right? So what we can do is we can add a no good in case it has multiple of these solutions, add that back to the CP problem and ask for the next most likely assignment to each of the digits. So that's what we did. So the baseline is the one that I showed before, where we do independent predictions and then solving. Hybrid 1 is where we do maximum likelihood optimization, taking just the constraints into account. So then we get an image accuracy of 99.69%. So even though we didn't modify the learning, right? So the machine learning model is identical, still our constraint reasoning can correct for 5% of the mistakes, almost 5% of the mistakes that the classifier is making. And if we then use this additional knowledge that the solution has to be unique, we can further increase, we can further correct some more mistakes that would be done otherwise. So we get a 99.72% accuracy here. All right, so that was my third example. Let me check my timing. Of how to add perception into the mix. Now, complex environment. This is also a very nice topic. So here, the whole idea is that we want to do predictions of something that is very difficult to estimate and then optimize over those predictions. For example, we want to predict historic energy prices based on weather forecast, wind forecast, and so forth. Or we want to do steel plant manufacturing, so optimizing the sequencing of orders by predicting the kind of defects that may have been happening on the slabs. Or we want to optimize a certain money transport, where we want to predict the amount of coins that are at each client so that the vehicle will not get overloaded or is less likely to become overloaded, and so forth. These are all examples. And again, the naive thing is, well, let's first predict, for example, the energy prices for the coming hour, for the hour of the coming, for each hour the coming days, so the coming 24 hours. That means that we get 24 predictions. And then let's optimize some job over that 24 hours, given these expected energy prices. Now, if we would use something like mean square error, which is a traditional loss function in machine learning, then on some example cases, what we've seen is that even though that the machine learning might think that it's improving its learning, so the mean square error continues to go down as we do this gradient descent learning. So this is in a deep learning framework, just a standard gradient descent. So the learner thinks it's improving on its predictions, but in fact, if you look at the regret, so if you look at the effect on the optimizer, then we see that the optimizer is doing worse and worse and worse and worse. All right. So the question here is, again, can we do this better? Can we maybe learn the predictive model using information from the optimization? So as I said, the MSE loss function is not informative enough. And the regret that's being shown here is by comparing the solution that we get if we optimize with the true unknown cost, so on historic data. If we compare the solution to the solution where we optimize with the predicted values, and we take the difference of the objective function when taking the true costs into account. And so what if, so the true cost is what you're actually going to pay, for example, in an energy-aware scheduling problem. And what's the difference in cost if you would have known what the prices are versus if you used your estimator of what the prices are. And so we really need a loss function based on the outcome of the optimization. And so the grand goal here is to do end-to-end learning where we can use this regret, this function here, as a loss function. However, we cannot directly use regret as a loss function in a gradient descent setup. And the reason is that the regret is discrete. And we have to solve the scheduling problem over a discrete decision variable, so it's discrete and hence non-continuous, and hence we cannot take the gradient. Another complicating thing here is that each regret computation requires solving an optimization problem, which may be NP hard. For example, in scheduling, we're solving NP hard problems all the time, so we have to do this for each one, as well as being non-differentiable in general. So how can we still use something of the task loss as regret? So we've been working on this problem and together with the people at Melbourne for quite some time. And we have, so we first tried different ways of approaching the problem, for example, using coordinate descent, making links to learning to rank, using dynamic programming to estimate it more precisely. But now we're looking more and more into using standard deep learning gradient descent types of approaches and finding out loss functions that are compatible with these advanced gradient descent machineries. And so I will talk about this last one here. So of course, we're not the only ones working on this, and nowadays there's been a range of different approaches proposed, and we can separate them into approaches that assume that they don't know how the solver works, so using a black box solver or a white box solver. And within the black box solver approaches, there's the SPO approach, smart predicted optimize, which is one of the first methods that arrived and that we started playing with. And so this one, what it does is it takes the predicted values and it takes a convex combination of the predicted values with the real values and it optimizes over that. Now I see I'm getting into a bit of timing issues, but let me still give you a bit of a hint of this. So this is the kind of batch gradient descent thing that we do. We sample some training data, we compute the predictions, then we do this optimization over this convex combination of the predicted values. And then we take the difference between the real solution and the solution that we got if we take these perturbed predictions, and that we use as a subgradient to update the loss function and so forth and so forth. And so this works quite nicely, but we have to solve our optimization problem for every training example. So if we're doing 20 to 50 epochs with 500 to 5,000 samples, we're doing thousands and thousands and thousands of solver calls. So the question here is, if we want to do the learning better, maybe we should look at how to do the solving better. And the way, of course, the computation time is high. Well, here we started from two observations. The first observation is that for these optimization problems, the constraints are always the same. The only thing that changes is the cost factor. And we solve this thousands of times. And for each training instance, the true optimal one can be slightly different. And so it's not true that there's a single global optimal one for all the instances. It can be different, but still only the cost factor changes, right? It's a question that we asked is, well, do we actually need to solve the MIP to optimality, or can we even just replace the MIP, because we're using MIP solving in this case, by the LP relaxation, because the LP relaxation already gives a hint at the direction that the predictions are giving you to. And then if we're going to do LP relaxation solving, well, we know that we're going to solve them thousands and thousands of times. And we also know that when we solve an LP, what we actually do is, in case of simplex, we repeatedly find an improving basis. So instead of doing this all the time from scratch, maybe we can warm start from previous bases. Right? So these are the kind of ways that we could improve the solving.
Yes.
Yes.
Just to warn you, I think we have a very tight schedule. So maybe if you, we have a few questions for you, but maybe
yes, I'm going to wrap up.
Okay.
All right, I'm going to wrap up. So this actually works. It's nice. It actually works on large scale instances. It was the first method that works on really large scale instances. And so these are the key takeaways: maximum likelihood, keep improving both the learning and the solving, and it actually becomes possible to do this hybrid prediction optimization even on large scale optimization problems. That's it.